Hello all. We are back to do more particle motion, specifically free fall motion, and today I want to look at a problem with you where you were not given the initial equation. So the last time we talked, I said that if you're given a position equation, you take a derivative, you get velocity, you take a second derivative, you get position, you're good to go. Okay, so if you are not given an equation, then we need to come up with one. And we can do that based on our knowledge of free fall motion and our knowledge of derivatives and how they work, right? So if I look at what they gave me, I know I have an initial position of 640 feet. So it's a shot upward from the top of a 640-foot building. So when the arrow is shot, its initial position is 640 feet above the ground. And it's shot with an initial velocity of 48 feet per second. So here's what I know. S of 0 is 640. If I plug a 0 into my position function, I should get 640. And also at the time of 0, my velocity should be 48 feet per second. So I'm going to use this to figure out what my equation has to be. Okay, so let's start with this. I know that for free fall, my equation has to be quadratic because that's what free fall equations are like, right? The reason we know that is because when I take my second derivative, I have to end up with a constant. And I even know what that constant's going to be. My second derivative, acceleration, is going to be the acceleration due to gravity. Now, this is feet per second. Based on the units, I know that my acceleration is going to be negative 32. So when I do my second derivative, I need to end up with a negative 32. Okay, that's going to help us here in a minute. So, I know this is going to be negative 32. Okay, so here's what we know. If I plug a 0 into this initial equation, I need to get a 640. Well, there's only one way this happens. I don't care what these two numbers are. If this is true, then this number right here is going to be a 640. In other words, if you plug a 0 into a quadratic equation, the number you're going to end up with is the number at the end. So if my initial position is 640, then that has to be the number at the end here. Okay, so I know when I take the derivative of this, I'm going to get 2 times whatever number was there, plus this number that was here, right? The 640 will be gone. Well, let's see if we can figure out what goes in that blank. I know that when I plug a 0 into my velocity function, I'm going to get a 48. So when I plug a 0 in, that's going to go away, and this number better be a 48. So I'm going to go pop that up here. That's got to be a 48. And last but not least, when I take the derivative of my velocity function, it's going to be 2 times that number that was originally in front times t. So when I take the derivative, it's just going to be 2 times whatever that number was. So guess what? This number right here must be half of the number I know I need. So in this case, that would be negative 16. So I can go back up here, negative 16. So by knowing a little bit about free fall and a little bit about how derivatives work, we can get our initial equation and then from there flush out what our other two must be. So if this number is negative 16, then this number right here is going to be a negative 32. So my position function is going to be negative 16t squared plus 48t plus 640. When you take the derivative of that, negative 32t, I'll write the t, plus 48. So that when I plug a 0 in here, I get 48. And then when I take the derivative of that, it pops out to just a negative 32, which I know is true because I have constant acceleration. So just from those two numbers that they gave us and a little bit of knowledge of how derivatives work, we can pop our 3 equations. Okay. Once we have our 3 equations, we can answer all kinds of questions. All right, the calculus is over. We've done the calculus. Now, all we're talking about is a little tiny bit of, I guess, physics and some algebra, right? So, one of the first things I want you to notice in this question is to find the average velocity. Anytime you see the word average, we're not talking about calculus. There's a difference between average and instantaneous. Instantaneous is calculus. That's the derivative. That's the equation of the tangent line. That's the slope of the tangent line. Average is not. Average is a slope of a secant line. Okay. So if I want average velocity, all they're asking me for is a change in position over a change in time. That's all they're asking me to do. So all I need to know to find an average velocity of this arrow is figure out how its position changed over this time interval. Now, I know how much the time changed. The time changed by 3 seconds. To figure out how much its position changed, I'm just going to go check out my position function up here. Where was it at 2? Where was it at 5? So S of 2 versus S of 5. All right, so S of 2, negative 16 times 2 squared plus 48 times 2 plus 640. So this is, let me write that out for you, negative 16, 2 squared plus 48 times 2 plus 640, and my handy dandy calculator tells me that is 672 feet. That's where it should be. Okay. If I do that same calculation, times 5 squared plus 48 times 5 plus 640. If I do that same calculation with a 5, and I don't typo it like I just did, so negative 16 times 5 squared plus 48 times 5 plus 640, I get 480, which is the number I wanted. Okay, so where did it go between 2 and 5? It was at 672 and now it's at 480. Now let's be really careful. The change here is negative. It went from 672 down to 480. So the number I want to put up here is 480 minus 672. Now how do I know that? We're talking slope here, right? So remember the old formula y2 minus y1 over x2 minus x1, right? So the 672 goes with the 2, 480 goes with the 5. So if you're going to do 5 minus 2 down here, then you better up here be doing 480 minus 672. Just pay attention to that. Again, it's an algebra thing, but it's a thing. 672. So 480 minus 672 gives us a negative 192 over 3. So that is a nice velocity average. The line over it makes it average of negative 64 feet per second. No calculus. People miss this question because they take, I don't know what, sometimes people take the 2 and put it in here and the 5 and put it in here and then add them up and divide by 2. Nope. Average velocity is the slope of a secant line. Instantaneous velocity is the slope of a tangent line, which is a derivative. So this equation is going to give you the slope of a tangent line at any point. If you want the slope of the secant line, then you need to identify 2 points on the position function and find the slope between them. All right. The arrow's instantaneous velocity at 5 seconds. That's actually an easier question for us because this velocity function that we have here is instantaneous velocity. So if I want the instantaneous velocity at 5, all I need is v of 5. So I'm going to do negative 32 times 5 plus 48. So negative 32 times 5 plus 48 gives me negative 112 feet per second. This tells me something. At 5, this thing must be headed back down. So they ask me about the motion of this thing. I'm going to say that at 5 seconds, it's going 112 feet per second, and it's moving down. The fact that that velocity is negative tells me it's moving down. So this thing was launched from a height of 640, right? Left here at 0, it went up and then came back down. That 5 seconds must be somewhere in here on the way down. By 5 seconds, it's on its way down. Okay, I love this question. Find the arrow's acceleration at 5 seconds. They can say find the arrow's acceleration at any time that it's actually in flight. We know the answer. A of 5, A of whatever is negative 32, and we put units on it, feet per second squared. It is really, really, really important that you're putting units on here. On open-endeds, we never know when there's going to be a point for units and when there's not. Sometimes, like part A will have a point for units and part B won't. Sometimes at the end, there's 1 point for all 3 parts, and you have to have all 3 parts of your units correct or you don't get the point. So it's a really good idea to focus on units. One of the things I say, and I don't even practice what I preach, but it's a nice idea, is that if you're not given units, just write like units. Like if you weren't given distance units, right, like units per second squared or something. I don't actually end up doing that because I'm not that like tedious and disciplined about my math, but it's a nice idea that you would do that. Or like if it's an area, write units squared. If it's a volume, write units cubed, just to get yourself in the habit of always looking for units. If they give you units, you have to return units. If they don't give you units, then you don't have to return units, obviously, but it's a good idea to just get in the habit of always paying attention to what the units are. Okay, so we want to know how high the arrow goes here. So one of the things we talked about, yesterday was this idea of maximum height. So I know I leave this height of 640, thing comes up, it reaches some maximum height, and then it's going to come back down and hit the ground. Okay, what we want to know is what that height is right there. Okay, so I know it's bigger than 640, right? But I also know something, that at maximum height, I know 2 things. That it's at, in this case, I don't actually know 2 things. I was going to say that we know that it's half a flight of time, but you notice this trickery here. For this arc, this would be half the time. But then once it gets back to this level, there's some more time in there, so we would have to be careful about that. How high the arrow goes, we also know that at the top, the velocity is 0. So if we want to know how high it goes, the first thing we need to know is when that happens. Well, I know that it happens when the velocity goes to 0. So if I take my velocity equation, I set it equal to 0, that's going to give me the time when the velocity goes to 0. So negative 32t is equal to negative 48. Which is 1.5 seconds. Okay, now, that's not what they asked. They asked how high it goes. That is just when it goes that high. So let's go find out where that is. Now that I know the time, I can find the position at that point. So I need S of, I shouldn't have written a t there, 1.5. I need S of 1.5. So negative 16, 1.5 squared plus 48 times 1.5 plus 640. All right. So negative 16 times 1.5 squared plus 48 times 1.5 plus 640. It is at 676 feet. So S of 1.5 is 676 feet. All right. So if this was 640, this is 676. We know it took 1.5 seconds to get there, which means that we also know that it took 1.5 seconds to get there. So at this point, I have a lot of information about this thing. It left here at time equals 0. It took 1.5 seconds to get up to a height of 676. Then it fell back down, took another 1.5 seconds to get back to a height of 640. So at this point, I've got a flight time of 3 seconds right here at that point. All right. Then, of course, it has to fall further. All right, last question. Determine the arrow's velocity when it impacts the ground. Okay. So many times we see people answer this question with the good old-fashioned 0. It just hit the ground. Please. I mentioned that yesterday. Don't be that person. Don't do it. Okay. It has velocity when it hits the ground. That's why if you did this with the watermelon would smash. If it didn't have any velocity when it hit the ground, it wouldn't smash. It would be a healthy, delicious watermelon when it hit the ground. Okay, so there's definitely a velocity at this point. We just have to figure out what it is. Okay, so if I want to know the velocity when it hits the ground, I need to know when it hits the ground. That's the first thing I need to know. Okay, so if this right here is a position of, if that right there is a position of 640, right here, then down here is a position of 0. And we already figured out that all the way up here was what, like 676 or something like that? So if we can figure out when it has a position of 0, not a velocity, but a position of 0, that's going to tell us this spot right here. So if I take my position function and I make it equal to 0, so I say S of t is negative 16t squared plus 48t plus 640, that has to equal 0. If I do that, I can actually simplify this out pretty nicely. I can divide through by negative 16 to make it easier. That's going to come out then to a negative 3t, and I believe that comes out to a 40, but it needs to be a minus 40. Okay, that, happily, even though it doesn't look like it at a glance, it's factorable because I can make a 40 with an 8 and a 5. So if I do a minus 8 and a plus 5, that will give me my negative 3 in the middle, and it tells me that I have 2 possible times when its position is 0. 8 seconds and negative 5 seconds. Clearly negative 5 is not going to be in the realm of possibility here. In other words, we're saying 5 seconds in reverse would have put you here. Now think about that. We said it's a symmetrical path, right? And we already said that it was 1.5 seconds on the way up and then another 1.5 to here. So at this point, we're at 3 seconds, right? Another 5 seconds puts us back on the ground at 8. So it's reasonable to think that this distance would have been 5 seconds as well. So now that I know that the time that it hit the ground was 8, all I have to do is go put 8 up in my velocity. Now, if I don't get a negative, we're going to be in trouble, right? Because obviously it was moving down at that time. Pretty sure I'm going to get a negative here. Minus 32 times 8 plus 48. We get negative 208 meters per second. And a smiley face. Okay. Again, the two questions, velocity questions always trip people up on these. The first is average velocity, thinking that you have to do something calculus-y, and you don't. Average velocity is a change in distance over change in time. Find the displacement over that interval, divide by the time. And then this velocity when it hits the ground, it is so important that you realize that that's not a 0. That's a position of 0. Depending on the situation, it's probably going to be a position of 0, but not a velocity of 0. Okay, I hope this helps. You should be able to use this kind of strategy to revisit numbers 5, 6, 7, 8 on the particle motion problems from last week. See you later.